Hello. So today we're going to go over the solutions for the Bellringer 2. Let me know if you have any questions. I'm going to post this video on YouTube. So the first question says, state the formal definition of continuity at a point x equals a. So like I talked about in class, there is an epsilon delta type of definition, but we're not really going to talk about that in this class. We're focusing on the three-pronged definition of continuity that we'd seen in lecture. So intuitively, we know that continuity means you can draw without picking up your pencil, but there has to be some more strict conditions, and those conditions are as follows. The limit as x goes to a of f of x is defined, or some people will say exists. F of a exists, or maybe I'll say is defined slash is exists. And finally, since we know that they exist, now I can say that f of a equals the limit as x goes to a of f of x. So basically, the limit exists, the function value exists, and they're the same thing. Now, let's check the next one. Is it continuous? Well, we know now what the conditions are. So we need to first check. Is f of, in our case, a is 2, so is f of 2 defined? Let's see. If I plug in 2, I'll get 5. So yes. So now we need to show, or we need to check, is 5 equal to the limit as x approaches 2 of f of x if this guy exists. So first we need to check if it exists, and then we can make sure that they equal each other. So first, let's check that they exist. So as we go from the left-hand side, the limit we'd have to check here. So that would be 2 squared plus 1, which is 5. Now on the right-hand side, we take the limit of this function, which would be 3 times 2 minus 1, which is also 5. So since the left-handed limit and the right-hand limit are equal, the two-sided limit is equal, or I'm sorry, is defined, and it's going to be the whatever they are equal to. So we can write the limit as x goes to 2 of f of x is equal to 5. And notice f of 2 is equal to 5 as well. So since they're both equal to each other, we could say yes. Now, give an example of a function that's not continuous at 0 and why it's not. So we just have to make it where any of the three conditions are not met. So one example would be a function like this. So I'll draw it in blue. We have a line. At 0, there's a hole, and we keep going. So here, it's not defined at 0 because there's a hole there, and thus it's not continuous. Next, what does the squeeze theorem say in your own words? So squeeze theorem is, like we talked about the two cops and a drunk, right? You have some random function that does something, but this is kind of hard to investigate. But I've got some function that I know is always below, and I got some function that I know is always above. So maybe I'll do something like this. And then maybe this was I'll redraw this black guy. And this black function is a little more tricky to understand, but the red and the orange, they both are simpler for us to understand, and the limit of the red is equal to the limit of the orange, and since the black is in between, the limit of the black also has to be the same thing. Now, what does it say in your own words? Basically just if f of x is less than or equal to g of x is less than or equal to h of x, and the limits of these guys are equal to each other, the limit of as x goes to a, then the limit of g is equal to that as well. I'm not going to write that all out, just talking because it's not enough space, but we've talked through the question. And now let's try and use the squeeze theorem to actually do this, to evaluate the limit. So here I have x squared times cosine of 1 over x. Notice that if I was just to do the naive kind of brute force approach and just plug in x equals 0, I'll get 0 squared times cosine of 1 over 0. Cosine of 1 over 0, 1 over 0 is undefined, so we can't really take the cosine of 1 over 0. So we can't just, just do this. So we have to do some creative approach. So you can notice this cosine. I know that I have cosine of 1 over x, which is an odd function, or odd, strange function, But whatever it is, cosine always has to be between 0 and 1. I'm sorry, negative 1 and 1, not 0 and 1. Now I can multiply every single side by x squared, and I'm allowed to do that because x squared is always positive. So I have no problems about the signs. X squared times 1. So now we have, negative x squared is less than, this should be times x squared of cosine of 1 over x less than or equal to x squared. And then we can take the limit of everything. So we get the limit as x goes to 0 of x squared negative less than or equal to the limit as x goes to 0 of x squared cosine of 1 on x less than or equal to the limit as x goes to 0 of x squared. Now, this limit is what we're looking to find, so we can't really do much with that. But the left-handed limit, that one is just 0. I'm just going to draw an arrow down. And the right-hand limit is also 0. Because of the squeeze theorem then, these guys are equal to each other, and so we know the limit of the x squared times cosine of 1 over x is also 0. Next, true or false. Oh, and this is our last question. How about ice? So true or false, the squeeze theorem only applies when both bounding functions are continuous at the point of interest. Well, what do we require for the bounding functions? We just require that the limit at that point exists, right? We require that they're both, I'll write out so it's a little more clear. So we want the f of x is less than or equal to g of x, less than or equal to h of x, and if you check your lecture notes, it should say this, for all x except possibly a. X equals a. Maybe for all x in an interval containing a. So we don't really care what happens at x equals a. And when we do the squeeze theorem, notice we take limits, right? We don't need to actually evaluate the function value. So it only applies when bounding functions are continuous. We can say no. But generally, you're not going to see a squeeze theorem example where you end up using non-continuous functions. And that's the end of this video. Let me know if you guys have any questions.